Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be looking at interpolation, and we will be looking at Excel. So I have a set of data. This data is heat capacity of carbon dioxide at 1 atmosphere absolute. This did come from a textbook. Actually, it came out of John Giancopoulos' Transport Process and Separation Process Principles textbook. But what we have here is something where really I could use any of the techniques. And we're just going to estimate C sub P at a couple of different temperatures. And we'll do it, let's do 300 Kelvin, and I want something that's outside of the range, 250 Kelvin. So let's start with just estimating these two here. And doing linear interpolation, you can use the formulas out of the book, but honestly that's the hard way, because Excel has a function and we can use the forecast function to do this. And so we say equals forecast. And I should point out that we do have some options there for different types of forecasting that we can do. We're just going to use the basic forecast function. If you have an older version of Excel, you won't have those other options anyway. And so the first thing you do is you put in the X value. So I'm going to put in this case, my temperature. And then I'm going to put in the known Y value. So I'm going to choose the terms that are closest to, in this case, 300. So that would be these two values. So C sub P is my Y. That's what I'm trying to calculate. And then I'm going to put in the known X's that correspond to those. And I get a prediction of 0.84253. And since this data table here is for 3 sig figs, I should not accept more than 3 sig figs in my answer. That would be inappropriate. Okay, so that's great. What about if I wanted to do this for 250 Kelvin? Now I've just copied and pasted. I've got relative references on, which is great for the 250, but I want to move this to the two closest points. 250 is not between any 2 points on my data table. So I'm going to just simply move this to the two that are closest, but 250 is below this range. And so therefore, I'm going to use the formula. I can still use a straight line fit for my two closest points. In this case, this is called extrapolation. So interpolation means you're between 2 points from your data table. Extrapolation means you've gone outside of that range. Now, extrapolation is generally not a good idea. If you are not too far outside of the range, extrapolation can work. But when you get very far, so like if I wanted to estimate this for CO2 at 100 Kelvin, that would be a very bad idea. Now this is where thermodynamics comes into play, because I am assuming that it's still CO2 as a gas, and we all know about dry ice. So this actually, will form that solid phase at 1 atmosphere if I am just under standard conditions. So extrapolation is a risky business, but you can do it, and as long as you're not extrapolating too far outside of your data range, it probably is safe. Okay, so that's our linear. What if I wanted to do the Lagrange quadratic? For that, I'm going to need So from our previous lesson, this is the formula. And I need to use the three nearest points. So for 300 Kelvin, looks like maybe these three would be the ones that are closest. But whether I use these three or starting with 283 to 338 shouldn't make much of a difference. Now, using this formula is a bit of a pain in the neck. So I'm going to say that it's equal to f of x naught times x minus x1 times x minus x2 divided by x naught minus x1 divided by x naught minus x2 plus, and now I need to do this for all the others. I'm going to pause the video here and type this. Okay, so I have my expression typed here. One thing I want to point out is I did have an error even in my very first piece, is I did not point to b. Okay, so I needed, when I said f of x0, these are the column b values, and x's are the column a values, but x is in cell D3 at this point. So this is my function. If I hit enter, okay, yes, good. I got something that was near there. Usually if you make a typo, it's a doozy of a typo, okay, and you'll get some number that makes no sense. Okay, and I want to do this again for 250. Again, this will be extrapolation. I'm going to copy and paste this. Now this is going to be bizarrely wrong because I'm using numbers down here, and I need to be using the three that are closest. And so I'm going to just edit by moving each of these references. And again, I'll pause as I do this. All right, and so you see that I have, one of these is wrong, B5. There we go. Okay, so that's my quadratic interpolation. And the last thing we want to do is the curve fit. So to do that, all I'm going to do is take this and I'm going to create a graph. And when I do this, I want to format that so I can look at it a little bit more clearly. I'm really wanting to be able to see what my values are. Let's see, I want this to go from 250 to 550, that's good. And I want this axis that's good. Okay, I wanted to really be able to take a look at what I was doing here. And I'm going to insert a trend line, and we'll start with a linear, and I want to display the equation and the r² value. And let's look at this. And this straight line fit actually doesn't seem to be too terrible, but I see that there's a little bit of curve to this that seems to be uniform, so I don't think it's picking that up very well. So if I switch to some other choices, exponential is going to give me problems. That's worse. Logarithmic looks pretty good. I could also do polynomials, where the r² is perhaps better on that, but I think that logarithmic seems to fit what I remember seeing in C sub p's, although you also do see a lot of polynomials. And so it doesn't matter which of these you do. Let's choose the logarithmic. And again, you might have chosen the polynomial one, and that would be, of course, fine. And so if I want to do this, now then I have this problem that I've used trendline to predict my curve, but this isn't going to give me as many sig figs as perhaps you'd like. And so I can do this using the log of x and do the slope and intercept. So let's do that. So x in this case is the t. And I can do this for all of these points here. And then what I'm going to do is I'm going to say the slope and I'm just going to estimate the slope for all of my known y's, which is C sub p, and all of my known x's, which in this case now is log of t. That will get me the slope. The intercept is this. And although it may not look like it, I really do have lots more sig figs than what I had here. Okay, so now then if I want to use my curve fit, to do this, I'm going to use this model for the equation. So it's equal to this number here times the natural log of my temperature plus my y-intercept. And using the F4 key to add dollar signs on the slope and intercept, I can use this for both of these numbers. Okay, and again, you don't want to give more precision than is in the table. Now, at these numbers in the middle here, this actually looks like a really good fit. But let's take a look at our graph. This slope really doesn't look like it's going down as steeply as this logarithmic curve fit predicts. And so I'm thinking that for the extrapolation, this is a poor choice. For extrapolation, you really want to look at your curve and make sure that it logically makes sense. And so I would select to use these answers, but in between, I think this smoothing might in fact be better. So it's up to you, but you have now seen demonstrations of different ways of doing interpolation in Excel. Thank you very much for your time.